Okay, so this is supposed to be a very high level presentation about what I've been working on the last year, what Slab does in general. Um, I was working on this with Greg, Zara, Emily, and Paul, and just jump right into it. We're working on end-to-end GNC algorithms validation for rendezvous and proximity operations, and we're using digital robotic twins, that test beds that are developed in the lab over the years. So I'm gonna start with talking about distributed space systems in general, the motivation for RPOD, state-of-the-art test beds that are existing in the world right now, and then our proposition for end-to-end validation using software and hardware components. So distributed space systems in general, all of us know two or more spacecrafts that are interacting with each other. They're trying to achieve some goal that otherwise wouldn't be possible using just one spacecraft. That spacecrafts could be cooperative and non-cooperative and try to achieve some goal. Why do we need more than one spacecraft? Some of them are just, I said that, impossible or harder to achieve with only one spacecraft. So this is kind of like an overview of the different distributed space systems that we currently trying to test for. Some of them are constellations, swarms, formation, flying, and rendezvous and docking. These are classified for intersatellite distance and also the navigation accuracy we would try to achieve when deploying these systems. Some of the applications, so some of them are very science-based applications, astronomy, astrophysics. You can see an image there from NASA mission, and it was trying to take an image of an exoplanet using a distributed space system. Earth and planetary science, also a mission that was deployed to try to more accurately estimate the gravitational field of Earth. I believe Professor D'Amico worked on that mission. Space flight and sustainability. So there's increasing number of objects in space, and we're trying to keep space sustainable for the incoming generations, and operations like we see on the bottom right are important to do that and deorbit some of the things that are currently on our way. And then some other maintenance in general, like replace batteries, refuel satellites. There's a lot of work been done in that area. So overall, the work in the Space Rendezvous Lab at Stanford, we're working on mission design, algorithmic development for GNC algorithms, decision-making algorithms, and then we use our test beds to validate our systems using high-fidelity numerical simulations and hardware-in-the-loop simulations, and then go through a full life cycle of a mission to embed those systems. And currently we see an image of the Starlink mission that some of SLAB members worked on some of the navigation algorithms that are tested in orbit right now. So the motivation for a rendezvous proximity operation, docking, and formation flying, as I mentioned, there's an increased number of resident space objects, and currently space logistics require high level of autonomy, mission or low Earth orbit, continuous grind monitoring. It's like expensive, there's time delay, and we want to achieve a high level of autonomy as high as possible. For software in the loop simulation, we want to be able to test our algorithms through numerical simulations, and we want them to be very effective so we can enable rapid prototyping for these algorithms to like do design iterations, and we want that process to be as fast as possible and as effective as possible, low cost. And then we also use software in the loop to create data sets for data-driven methods. For hardware in the loop simulations, so only software is usually not enough. We cannot capture all the hardware imperfections with like sensor noise, delays, generally things that you can't capture just through numerical simulations. But also hardware is not enough because we can't usually simulate the full mission profiles for space missions due to obvious physical limitations. So we're trying to complement each other and do numerical simulation with software and then embed as much hardware as possible to kind of bridge that gap between software world and the real world in space environment. Current state of the art test beds in the world, some of them I kind of classify them here to software based and hardware based. So you have ballistics, yeah, basilisk, celestial object simulator, Genoptic, optical skyfield simulator, and others. Those are usually those are just software based. And we have the Space Center in European Proximity Space Operations Simulator, EPOS, Lockheed Martin's Space Operations Simulator Center, and we have others. Um, the problem with some of them is that some of them only apply to close range, some of them only apply to far range, some of them only use RF-based methods for navigation, some of them only use vision-based. And in general, some of them are just not as accurate as some of the test beds we have here at SLAB. The proposed framework, we want to combine software in the loop and hardware in the loop in a unified pipeline. So here in the block diagram, we have kind of general idea. So we have initial conditions that are going through a high fidelity simulator for dynamics and attitude profiles. Those go into either an OpenGL renderer that provides some data for the vision-based systems, or into a signal simulator that then goes through either a vision-based system or a GNSS receiver emulator that goes then into our GNC stack and then goes back. So the general idea is to seamlessly replace these software components with the hardware components and to bridge that gap that comes from only numerical simulations. And then the idea is to support uh, missions across all scenarios, so near range, mid range, and far range simulations. And then we ideally want that process of replacing each other to be very easy so we can test modularly and just replace different components. So overview of our digital twin is known as the RPO stack of SLAB. We have a GNSS signal generation and emulation. We have a vision-based sensor simulation via OpenGL rendering. And we have an inter-satellite communication modeling. It is a high-fidelity modeling that includes the delay and dropout to kind of match as close as possible for real life scenario. It is faster than real-time execution. So as I mentioned, we do want to be able to simulate fast to like rapid iteration of our algorithms. And then just for scale, we can simulate 3 days of GNSS data. We can generate that in about 20, 30 seconds and test that. And then we can reiterate and modify our navigation algorithms, control algorithms, and that helps for the faster design process. And in general, it just enables a quicker debugging and implementation level, and in general to like spot problems in our algorithms. So this is the overall architecture of the GNC stack. We have right here the navigation module, management, safety module, and control. These are control algorithms developed at SLAB over the years, navigation algorithms that are also developed at SLAB over the years. We have vision-based algorithms. We have such as SPN, which is spacecraft pose network. So we use deep neural networks to estimate pose. We have N-Gilon navigation, which is also a vision-based methods. And we have other GNSS methods as well. And for the controls, those are also developed SLAB, different control algorithms, different solvers that we're trying to assess their accuracy. Here we have exchange data, external systems, but we're mainly going to focus on the navigation, control, safety, and management modules to validate our system currently. In terms of robotic twins, so one of the test beds for vision-based systems, the optical stimulator. So we use that uh, to validate our vision-based far to mid-range scenarios, close range as well. We replaced the digital camera model with the same star tracker in hardware deployed in NASA's Starlink mission, and that helps us minimize the gap between simulation and real world. And this was used to test some of the navigation techniques developed by SLAB students that are currently also flying on Starlink mission. For close range navigation, we have Tron. So this is a test bed for rendezvous and optical navigation. We use two robotic arms to simulate two spacecraft, a chaser and a target. We have 6 degrees of freedom in each, and a linear array that adds another degree of freedom in the chaser robot. We have light boxes that simulate Earth albedo, and we have Vicon cameras that track motion of IR markers that are located in both the chaser and the target objects. We use these for both close range navigation for close range navigation with vision-based techniques, mainly deep neural networks. And these are also used to generate big data sets that are shared with other researchers in the world to keep trying to push the state of the art for navigation algorithms, specifically for data-driven methods. The last hardware testbed that we have is Grand, which is a GNSS generation simulator in closed loop, and these are for RF-based methods. We see here the IFN GNSS generator goes into a flat SAT that is the same processor, same Linux kernel, same communication ports that will be deployed in space in real mission. And then again, we have the dynamics that goes into that simulator, and then it goes back, and that enables us to test our RF-based navigation algorithms on hardware. Some of the results in the Tron facility calibration process. So we use Bayesian data fusion approaches. So for robot world hand-eye using vision-based measurements with Charuko boards, but also Vicon cameras and KUKA measurements are fused together to get better calibration results. Here are shown some of the previous work results on SPN-based navigation. So we see here that we expect in general to achieve lower calibration errors than the actual navigation algorithm errors, so that that enables us to say how accurate our navigation algorithm is versus the errors that come from our own testbed. And we see that these are indeed lower of magnitude less. For test scenarios, this is a near-range navigation scenario using SLAB's flight software simulation. These are an RTN frame of the servicer with respect to the target. And these are the delta V's applied throughout the mission, and we see it as an approach trajectory. These are software in the loop results for RF-based navigation using Artemis, using digital, one of the navigation modules that developed at SLAB. Yeah. These are to be filled. And then conclusions. So we develop an end-to-end novel framework to enable software in the loop and hardware in the loop. We validate our multi-modal GNC autonomy stack across all mission phases. So we do close, near, and mid-range navigation modules, and that helps us reduce cost and risk in algorithm development and testing, and it can support a variety of mission concepts from all phases of mission. Limitation and future direction. So we do still need to do some more work on error characterization from each of the test beds to again determine which errors come from our navigation control modules and which ones come from our own test beds. We need to work on closed loop simulations with Tron, semi-resolved imagery capabilities for higher software in the loop fidelity in the mid-range phase of the mission, and GNSS integration with Tron and in general using hardware in the loop. And yeah, that's it. If you guys have any questions.